We also have partially decoupled systems, and those are where one of the differential equations depends on the dependent variable of the other, but not vice versa. So let's take a look at a modeling problem, and we'll build a model and we'll see why this becomes partially decoupled. But I'll give you a quick example here before we get into this of what a decoupled equation would look like. This system right here would be considered partially decoupled because, as we can see here, the value of the rate of change of x, it only depends upon itself. And so it is decoupled from y. It does not have any, there's no y value affecting the rate of change of x. But if we look at the y, or dy dt, then we need information about x and we need information by y. So in a way they are kind of coupled, but they're only partially coupled because only y, the rate of change of y depends on x, but the rate of change of x only depends upon x. So let's suppose that we have two buckets, and I'm just going to kind of draw these two buckets. So here's a bucket, and then maybe here's another bucket. And what we have going on is we have the first bucket receives water at a rate of 3 gallons per minute with a concentration of salt of 1/4 pounds per gallon. So what we have coming into this bucket, and it doesn't really matter where we draw this arrow, but we have 3 gallons per minute concentrated with 1/4 or 0.25 pounds for every 1 gallon. So if you think about this, if 3 gallons come in every minute and you get 1/4 of a pound of salt for every gallon, so in 1 minute you're going to get 3/4 pounds, and that comes out to 0.75, which is the same thing as multiplying these together. What we have going out of this bucket is water flows out of the bottom of the bucket at the same rate into the second bucket. And I suppose to make this drawing a little bit more conducive to reality is let's bump this down a little bit so it looks like we're using the effects of gravity. And so what we're going to have is we're going to have this outflow coming into this second bucket, and it flows out of the bottom of the bucket at the same rate into a second bucket. So the water is going to still come out at 3 gallons per 1 minute, and that should tell us already that the water level is going to stay the same. The water level is neither going to rise nor fall. From the second bucket, the mixture flows out to another source at the same rate. Salt water comes in. Both buckets initially contain 5 gallons. So let's refer to some, and then so out of here we're going to have 3 gallons per 1 minute as well. So this is hopefully looking familiar as a modeling problem, at least with the initial bucket. And then for the second bucket, we'll kind of have to do the same thing. So we're going to define our variables here. Let's go ahead and call x. Let that be the amount of salt in bucket 1. That's going to be measured in pounds. And we'll say y represents the amount of salt in bucket 2, again measured in pounds. And t is going to be time in minutes, since we started pouring this salt solution in. So when we're going to try to model two rate equations. One's going to be dx dt, and the other is going to be dy dt. So dx dt, based on my definitions for x and t, it has to be in pounds per minute. Okay, so this is going to be a similar modeling problem. Here we if we multiply gallons per minute times pounds per gallon, we're going to end up with pounds per minute. And so this equals, let me go do this in a different color, this equals 0.75 pounds per 1 minute. And so that's what I have actually coming in, which is 0.75 pounds per minute. And then what I have coming out, well, I have 3 gallons per 1 minute. As we've already mentioned, this is x, the amount of salt that's in the bucket. That's already in pounds. And then we should also point out that these buckets are always fixed at 5 gallons. So x is, in terms of the flow rate, I have 3 gallons per 1 minute. But I can't just put 3 here because that measures gallons per minute, not pounds per minute. So I need to multiply this by some number of pounds per some number of gallons. Well, that's just my concentration of what's inside the bucket. What's coming out is a function of what's inside. What's inside of here? Well, at any moment, there are X pounds. And we can't say it's a quarter because, remember, there's stuff coming in and stuff coming out. So this is constantly mixing, and at any given moment, it's impossible to say exactly how many pounds there are in there without doing some calculus analysis. And so there are X pounds dissolved in 5 gallons. And you can see here we get pounds per minute again. So we have 3x over 5, or 3/5 x, which is 0.6x, and this will be in pounds per minute. So this will be my 0.6x. For dy dt, we're going to do a similar analysis. But for dy dt, what's coming in to the second bucket is actually exactly what is coming out of the first bucket. So this arrow here comes out of bucket 1 and enters bucket 2. So the inflow is the outflow of bucket 1, and that's going to be a positive 0.6x because 0.6x is coming in to the second bucket. And here I have to do the same analysis I did up here. That should be pretty straightforward for us to write. That's going to be y pounds. So what's coming out of bucket 2 is there are y pounds mixed evenly throughout 5 gallons, which will, again, in this case, will give us 0.6y. So this equals 0.6y pounds per minute. And then lastly, I will just subtract away that 0.6y here. And you can see now that we have a decoupled system. A partially decoupled system. That is, we notice that the rate of change of x, dx dt, only depends on x, but dy dt depends on both x and y. So we want to eventually solve this, and we'll do that shortly, but let's just write the structure of these two equations. So this means that dx dt is only a function of x, and dy dt is a function, some other function, not the same one. It's obviously different than this one up here, but that's a function of both x and y. Notice that neither of these depend on t. And we're going to keep it that way for a while, because once you start involving t in those equations, things can get a little bit more hectic. So there's our model, and now we're thinking, well, how do we solve this one? Because in order to know anything about solving dy dt, I have to know what x is. But the beauty of having a partially decoupled system is that I could solve dx dt first, get x, and then substitute that function in for x down here. So we're going to do that in just a moment here. We're going to say, first, step 1 will be solve dx dt to get x, substitute x into dy dt, and solve for y. So that's pretty much all we need to do in order for this to take place. We call this a partially decoupled system because the ODE for bucket 1 does not depend on the amount of salt in bucket 2, but the amount of salt in bucket 2 does depend on the amount of salt in bucket 1. If these were reversed, if dy dt was only a function of y, but dx dt was a function of both x and y, then we would call this still a partially decoupled system.